you have accepted our invitation that you will be giving a talk, and he was so excited, and he was just remembering the days when you were doing PhD together in Minnesota and all, and how you were. So it's such a small world, and then he was just he just got back in time, and just was recollecting all the moments spent with you.
well, he's a lovely person and
yes,
wonderful scientist, of course.
But, we were very fortunate to have him as a guide.
No. Yes, very soon Prashad, GVR Prashad will visit us here.
Oh, really?
Yeah, because he's in Chicago at the moment on Fulbright Fellowship, and he will come end of next week. He and his wife are visiting. So.
Oh, that's very good.
Yeah.
So I think GVR Prashad was his first student. I was one of his last students.
Okay.
So my work was only in this low Miocene formation, Kasauli formation, equivalent to Murray's, lower Murray's, upper Murray's. And
I see.
So a lot of work I did that is about plant fossils. Flower and Robert Spicer visited, and
yes.
So he taught me taphonomy of those plants. So that was quite a relationship, we had that at that time.
Yeah, no, Spicer, very good, paleobotanist, and very interesting work on uplift and these things. Yeah.
And then I was in Ladakh. Then I shifted to groundwater and doing some experiments in the Indus Switcher zone and across the Indus Switcher zone in Karakoram range.
Right.
And but I kept collecting a lot of fossils there also.
Yeah, good.
So this is it. So maybe we can just start in a minute or two.
Yeah. So what would you like to do today? I mean, today this is a practice, right? For the
practice also, but with Peter Monod also, we just we did directly, So at that time there was some internet breakdown, and then things didn't work out,
I see. Okay.
So you'd like to. So maybe I think if you are ready, then we can just record this. But but I think on that day, I think we will request you to give it a live. But in case something happens,
I see. Okay. All right.
Just for that purpose, I think we will just try to record, and if something happens, then we can just play this on, and you can just join, or maybe something. If not, then you just continue with the speech on that day. That I think that is what we think. If you think that it is okay, then that is what we have.
Sure. That's okay with me. Yes, no problem. Yeah.
So
okay, I have put the slides together, but I wasn't quite realizing that I would do the whole thing right now. I thought, but
no, it's okay, Nigel. If you're not comfortable, then we can just do it on that day also, that day only. But I think we just that we suffered that problem on that day, Then things didn't work out, and we were just stuck up in between, and then his connection was out because there was heavy snowfall and something that. And then, but luckily,
well, I think I can do it now, Ritesh. I can do it, and we can record, and then you have a backup. So, no problem. Okay, I think I can do that now. But one thing I would like to ask you that many of the people will not really have a geological background. Is that right?
No, but I think what we in Peter Molyneux, I think we were expecting about 20-25 because we were restricting it to only people who are interested in Himalayas or Tethys. But we were surprised that this Zoom meeting was for about 100 people, and they were not just able to log in. There was so much crowd, because we shared it with only maybe selected people, but they pass on, and then it was like a. So I think in that case also we got a lot of requests for your lecture also.
Okay. Yeah.
So I think we would expect a lot of geologists also and a lot of non-geologists also. But once we are thorough with this geological session, we are not going to leave you. Maybe for the museum, I'm more interested in how you can just make this story simple for the children who will be visiting us, in the museum.
Yeah.
So this museum I'm making in Kasauli, basically.
Yeah.
And then basically for the children, for about fifth, sixth grades, to popularize geology among the students. That is the aim of this museum. So I'll ask my colleague, Miss Oshin Gupta. She'll also come. Okay.
Okay. Yes. Yeah.
Oshin, can you just join us?
Let me just get some more tea here. We'll just be back in just a second.
Okay. Okay. Bye bye. Oh, that's fine. So I think. I think it's too early for you.
Great.
So she'll be joining us maybe in a minute or two.
Okay, I will just look at
the
slides I have here. How is the COVID situation?
Now it's almost over here. Now no one is like, we are taking some precautions. Yeah. But it's not like it's bothering anybody. Everyone is having that flu.
Yeah.
But I think now it lasts for about 3-4 days.
Yeah.
And gradually it fades down,
Yeah.
No problem. We are not facing any problem. My wife had this, but I think now she's okay.
Yeah, good.
So how is the situation there in your country?
Well, it is beginning to get a little bit back to normal. Now we are having all the students back on the campus and lectures and everything. People are wearing the mask, but yeah, it's beginning to feel like it's getting back to normal.
Normal, yeah. I think now it is not a big issue,
Hopefully it will. Yeah.
I think it was like somewhat yeah, there were a lot of casualties, but it was like a curse of modern science, modern medicine, you can say. Everyone who was hospitalized in our case, I think they were more susceptible, but those people who didn't care, they were okay, they just had some fever in the house, proper ventilation and proper care, and I think everyone worked. But otherwise, I think there was a lot of problem with the people who just went to who got panic and they just went to the hospital. So I think she's getting ready, I think. I'll just check with her. Otherwise, we can just start with your Hannah.
Yeah.
Maybe. So. Can you see your talk now on my background?
Yeah, okay. I can see Peter's talk.
This is Peter's talk. Oh, sorry. Just wait a minute. What is happening? Video. Yeah, just a minute. Yeah, sorry, my fault.
No problem.
Okay.
Oh, there we go. Yeah.
Yeah. Okay now. Yeah. I'll just check with her if she's coming, and then so the format will be she'll be introducing she'll be talking about you, introducing you about yourself.
Hello.
Okay.
Yeah, I'm encountering some error with my password. I'll just figure this out and be right in.
Okay. So maybe 1 or 2 minutes.
Yeah, yeah.
Okay. So Nigel, I'll just need your help also that I'll just share the pictures of the museum which you're making. And then we have divided it into about 10 sections. We have two halls. One is like the natural evolution, and then the other hall talks about the man and its impact on the environment. Theme of the museum is evolution and extinction, and from fossils to fossil fuel.
Okay.
So we are popularizing fuel also. It's not that bad, and as has been projected by the climate change scientists, So so what I want is like we got some posters from the internet and all about we have one section dedicated to the Cambrian explosion, and that section is about we have got some fossils from of trilobites, the blind ones also, and the with the eyes also, and then we are keeping some we are making some glass, microscopic glass, magnifying glass, and keeping at some distance. So that is how we are going to show it to the children, that these are the creatures, early creatures. But I am more interested in, we are making a huge poster of about say 5 by 5 feet, in which we will be we want to make it like very lively environment at that time when the explosion happened. The oxygen was coming, the water was there, and then how the unicellular organisms turn to multicellular organisms, and then the transition, and how could we correlate and make a beautiful picture of poster of that early section, and
yes,
we may need your help, in that. Maybe we can share what we are planning, and then Ocean is doing this graphic designing for the museum. So
right.
she'll be joining us, and then we will share. And we are in the process of making these posters now. Everything is complete now. Yeah. So the posters, the early life, and then what happened was like how the Edia Cara sorry, not the trilobite extinction around 330 million years. So this evolution and extinction of trilobites, we are going to show in the brains of the child that it was like evolution is happening and extinction is happening. Evolution is happening, extinction is happening, like right from the very beginning when the Earth started, like.
Yeah.
So okay, now she's there. Ocean.
Oh, hi. Hi, Nigel. Sorry.
Hello. Hi, Ocean.
So Ocean is our graphic designer for the museum. She's conceptualizing everything and making all the designs. So the Cambrian explosion and maybe the Precambrian explosion, Precambrian like Edia Cara and Stromatolites. So we are trying to make how water was the birth of, making topics like birth of water, the birth of life, the first life, the primitive life, then the early life, and something like this. The topic's very interesting. And the Cambrian, so now she maybe she's in the process of actually conceptualizing all the posters in her mind, so that she comes up with a concept, and maybe she'll be talking to you whenever required, or sharing some information or whatever information is required. And I request you, if you can spare your time and some thoughts and in designing that poster for the keeping children in mind, you know.
Yes, right. Yeah, happy to, of course.
No, thank you very much. Thank you very much, Nigel. So she's Oshin. Now you can just start Oshin, and we'll just give it a trial run. And Nigel has agreed that the problem which we faced with Peter when the connection broke, so we will have this talk as a buffer in case something happens. So we will play this. Otherwise, he will be presenting his talk live on that day.
Right. So should I begin with the introduction for Nigel?
Yeah. That Nigel, is it okay with you?
Yes, fine.
Yeah,
no problem.
Perfect.
Okay, the recording is on right now, or like
Just I think it's on.
Heads up on that. Okay.
It's on. Okay, yeah, I can just do it again. Yeah.
Nigel Hughes is a paleontologist and a stratigrapher specializing in early Paleozoic animal life and environments. He has worked extensively in the area of paleoevolutionary development, biology on trilobite ontogeny, and on the early Paleozoic history of South and Southeast Asia. In his early days of exploration, Hughes walked through the Himalayan region from Nepal to Tibet, looking for trilobites that could help him reconstruct when and how these mountains formed. He completed his doctorate at the University of Bristol in England and was also involved in a refugee project dealing with displaced people in West Bengal, India, where he lived for a year. He serves as professor of geology at the University of California, Riverside, and was the 2021 winner of the R.C. Moore Medal for Excellence in Paleontology. And I would now request Nigel to take over. Thank you.
Oh, thank you. Well, thank you very much for that very kind introduction and for this invitation to speak today. So let me just get my slides up, and so I hope you can see the screen. Is that
it's okay.
Yeah. Okay. Great. Well, thank you very much for this invitation. It's of course a tremendous privilege to be able to visit the Indian subcontinent and work on the geology of really the most spectacular part of the planet in terms of its recent geological history. So what I'd like to do today, hopefully without too much technical detail, but with enough to tell our story, is to discuss why the geology of the Himalaya is so important, and also particularly why the early history of the Himalaya, before India collided with Asia, why this early history and understanding it at the time, for example, when the Trilobites were living, is an important thing to study in order to have a more full understanding of the history of the Himalaya. So that relates, of course, to the initial formation of the rocks, and then their uplift, and of course the erosion. So that's the up and down part of the Himalaya. And of course, all this relates to the fact that our planet is a very active one, that heat energy being released inside the Earth is redistributed to cool the Earth down. And the way in which that happens, of course, is the movement of the rigid plates that make up the crust of the Earth. And the crust, of course, is solid, and the joints between these solid plates represent the places where they're moving apart, the mid-ocean ridges, and of course, the places where that expansion of the plates moving apart is being balanced by material being subducted, keeping the Earth roughly the same size. And of course, India's geological history is particularly exciting because of the movement of the subcontinent from its position in Gondwanaland northwards to its collision with Asia. And really, there's no part of the world that has such a spectacular, relatively recent geological history as the Indian subcontinent. And so here in this reconstruction, India, of course, was originally part of the supercontinent of Gondwanaland. This is a reconstruction showing the condition 120 million years ago. India and Antarctica and Australia have already rifted from Africa. That began about 180 million years ago. This is just the point where India is beginning to break away from Antarctica and Australia, and then begin its journey, moving at some intervals at 20 centimeters a year, a fantastic rate of movement northwards, ultimately to collide with India to form the Himalaya. And of course, this is a cross section looking at the northern margin of the Indian plate, as Peter Molnar so beautifully showed, colliding ultimately with Asia. Here comes the Indian subcontinent, and eventually the two collide and force up the Himalaya in the way that Peter described. What I'd like to look at and talk about for the academic part of the talk today is the condition long before India's breakup from Gondwanaland, and really close to the time that Gondwanaland itself formed. And this is the geography of the world as we understand it in the Cambrian period. I am speaking to you from California. This particular piece of California, who knows quite where it was when the Trilobites were living in the Cambrian. This, of course, is Scandinavia and Baltica, parts of where I come from originally, Britain over here, and of course the southern continents together as Gondwanaland, and India's position as part of the equatorial part of Gondwana in this region here. So what I'd like to stress is that during the Cambrian, the present western part of India, the west coast, was against Africa, and the east coast was against Antarctica. And the part of India, the Indian subcontinent, that faced the ocean at that time was the northern part, what is now the Himalayan mountains. And it is, of course, the breakup of Gondwana and the movement of India northwards that resulted in taking rocks which formed in that sea on the northern margin of India and forcing them upwards to form the world's greatest mountain chain. So I think we all know the physiography of India, the basic peninsular part of India, made up of rocks that are mostly very ancient, thousands of millions of years. The Indo-Gangetic Plain, which is really so young material that has been eroded from the Indian peninsular part and from the Himalaya, so no ages in millions of years there. And then rocks that have ages in hundreds to tens of millions of years in the Himalaya. And the reason for that, of course, is that that is the part of India that was marine, situation for accumulation of sediments on that coastline of ancient Gondwana. So if we look at the basic geology of the Himalaya that Peter Molnar described so nicely last lecture, I just want to give a very general picture of the gross geology of the Himalaya. And this is portrayed by what's called a lithotectonic map, which signifies the major groups of rocks and that are bounded, the junctions between, the boundaries between being major faults. So if we think about the material that is part of the Himalaya itself, south of Tibet, south of the Lhasa block of Tibet, there are really four major zones that occur within the Himalaya, each separated by a major structural discontinuity, a major fault, a major break, along which slip has occurred as India has moved forward and collided with Asia. Let's just talk about these 4 zones in very general ways. The most northern is called the Tethyan Himalaya, shown in blue. And this consists of sedimentary rock, primarily sedimentary rock, rocks laid down at the surface of the earth in layers. Then we go across a major fault called the South Tibet Detachment System or Fault System, and we enter the red zone, which is called the Greater Himalaya. And the Greater Himalaya is made up of rocks that are very highly squashed and deformed, metamorphosed rocks. Some of them were originally sedimentary, some igneous rocks, some cooled from magma inside the earth, igneous rocks, but they are highly deformed. To the south of the Greater Himalaya, the red zone here, is the main central thrust, a very important fault in India. And south of that, we go back into rocks that are primarily of sedimentary nature, called the Lesser Himalaya. South of that, the main boundary thrust, then we get into the Shivalik Hills that are so famous for your wonderful mammal faunas and all the lovely work that Ashok Shani and his colleagues have done. And then the Himalayan frontal thrust taking us really onto the Indian Craton. And you can see that I've got a little square here and a place called Dulmera. This is in Rajasthan. And the places, the names that are given here are locations in which Cambrian rocks have been described from these various lithotectonic zones. And what I'd like to point out is that of all the Phanerozoic systems, so the Cambrian, the Ordovician, Silurian, etc., the Cambrian is one that has the most wide distribution along within individual lithotectonic zones and across them. So you can see that there are many places, Poru Valley, Lidar Valley, Janskar, Spiti, Kamoan, even down in Bhutan, places where we find Cambrian rocks in these zones. And that's true in the blue zone, it's true in the Lesser Himalaya, the green zone, it's true in on the Indian Craton itself. So this is a great advantage because it gives rocks that were formed at the same time wide distribution, and we can therefore reconstruct what the northern margin of India looked like during the Cambrian time. So that's the journey we're going to take today and what I'm going to be primarily talking about. And the academic issue that has stimulated and driven our interest in this issue is related to how geologists think about the relationships, original relationships between these various zones. So this is a cross-section, Peter showed a lot of these, cross-section of the Himalaya from the south on the left to the north on the right. And I've drawn the colors showing those different lithotectonic zones. You can see the boundaries between them, the main central thrust here, for example. And what I'd like to point out is that in this important paper by Pete Desels in the year 2000, he argued something really quite interesting. And that is that these 3 zones here, the southern ones, were, in Peter's opinion, part of real India. But the 2 northern zones, the red zone and the blue zone, were part of a separate piece of continent called the Greater Himalayan terrain. And that the main central thrust, therefore, was originally an important boundary between material that was really Indian and material to the north that was something else, exotic, coming from some other place. And I'd also like to point out that in this idea, the idea is that the sedimentary rocks, the blue zone rocks of the Tethys Himalaya, are lying on top of the deformed rocks in the Greater Himalaya. So remember, the Greater Himalaya, the red zone, is these very squashed and metamorphosed rocks. The idea was that the blue zone rocks lie on top of that as an ancient landmass that's been buried by these sedimentary rocks. So what is the evidence for that? And here this is going to be the most technical part of the talk. I will show pictures of fossils after this, but please bear with me in this discussion for a few minutes, because this is really the heart of the academic questions that we've been asking. So what is the basis then for this argument that the Peter Dessels and the group from Arizona made? The argument is based on what is called detrital zircon geochronology. So imagine that we go to the beach and we collect a sample of sand. Most of those sand grains will be quartz, but within the sample, there's very likely to be some other minerals, one of which will be a very hard mineral called zircon. It's very hard. It forms from igneous melts, from hot rock melts. And when it forms, a little radioisotopic clock starts in the grain and tells us the age of that grain. Now, in sands at the beach, there may be thousands of grains of zircon that formed millions of years ago, and because zircon is very hard, have been washed around, uplifted, eroded, gone back into the sediments, washed again and again, and we can collect a sand, collect the zircons in it, and date some of those zircons, say 100 zircons. And the next slide I'm going to show you is a graph that shows the ages of populations of those grains, samples taken from the blue area, the red area, and the green area. And let's see how they compare. So this is the picture of that then. These is the numbers of grains on the y-axis here. If we've got a lot of grains, we've got a peak. If we've got none, we have nothing. And these are the ages of the grains from 0.4 billion years ago, 400 million years ago, right back to 3,600. And all that is important in this graph, I think you'll agree with me that there is one clear message in this graph, and that is that the sample from the blue zone and the sample from the red zone look similar. They have basically similar distributions, whereas the sample from the green zone is different. And the reason why, the main reason why the sample from the green zone is different is because there are no young grains in the sample. As you see here, there are young grains in both the Tethys Himalayan sample and the Greater Himalayan sample, but none in the green zone. And this, Peter Dessels considered to be a fundamental difference between these two regions. This green zone being true India and the northern two zones being something else, being exotic. But is that the correct explanation? Well, the distribution of these age of zircons tells us something about what material was building the sandstones, where the grains were coming from, grains of certain ages. But it also tells us something else. It tells us the maximum age of the sandstone. If instead of going to the beach and collecting a sand, we went to a section and collected a sandstone, we can do the same thing. We can take the zircons and date them. And of course, the age of the youngest peak cannot be older than the age of the sandstone itself. Sorry, cannot be younger than the age of the sandstone itself. So if we see, for example, that we've got grains 500 million years old, that sandstone could be much younger than that. It could be 100 million years old or 2 million years old, but it cannot be older than 500 million years. So these detrital zircons put a maximum depositional age on the rocks. So this difference between the green zone and the blue zone and the red zone, could it be because the rocks, the sandstones that were sampled, formed at different ages? Well, in fact, this is something that Tehsil and colleagues noted, because they noted that this sample was 1.5 billion years old. That sandstone formed 1.5 billion years ago. So it can't possibly have any young zircons in this age here, because the rock hadn't formed at that time. So a better thing to do to compare would be to have rocks that formed at the same time. And how can we tell that the rocks were formed at the same time? Well, using the traditional method, and that is using paleontology, using fossils that we know are Cambrian in age, and then collecting sandstones associated with those and comparing them. And when we do, this is the kind of answer we get. You see that in the green zone, the same part that is meant to be true India, we have lots of grains that are young in age. And so our argument has been, yes, there is a difference within the green zone between younger rocks, Cambrian rocks in this case, that contain many zircons that are just a little bit older than the Cambrian, say 500, 600 million years, 1,000 millions of years. But the big difference between any samples in this figure is between this one over here, which is extremely old, and this one here, both of which are in the green zone. So our argument is that using the power of paleontology to make sure you're comparing rocks of the same age, we can resolve this issue. Now, of course, that's not exactly how Peter Sells sees this, but we'll talk about that a bit more. Okay, so now let's do some more fun things like show pictures of fossils and talk about them. So the first thing to say is that, of course, I am by no means the first person to collect fossil trilobites in the Himalaya. There's been a long history of this extending back over 150 years. Many local geologists have contributed in very important ways to this. And this material is held primarily in the collections in the Geological Survey of India in Kolkata. This was a specimen that was collected from Kumaon by officers of the GSI in the 1980s. It's a trilobite. And of course, in the Himalaya, this is a region where the fossils get squashed, even in the blue zone where the sedimentary rocks are preserved. They are deformed because of the Himalayan mountain building. And so what we've tried to do here is to restore the shape, the original shape of the fossil, taking out that squishing. So I wanted to put this in to just mention that that legacy of work is extremely important, and museums are critical to this function of maintaining the knowledge that we do have and curating the original specimens. Most important function, and so important that your museum is being built. This is the GSI, Geological Survey of India in Kolkata, on my first ever day in India as a young man aged 18. We visited the GSI and I began an association that is a happy one that has been important to my career. I want to tell you one interesting, I think, story about a fossil that occurs in the collections of the GSI. that were collected by Sir Henry Hayden, shown here, and identified as a sponge by a scientist called Reed in 1910. And this is the specimen in the GSI. There's a 5 rupee piece for scale. And I must admit, when I first saw this, I knew it wasn't a sponge, but I thought it might be something inorganic, that it might be a mineral concretion of some kind. You can see these little lines here. There's a fossil, that's a Brachiopod fossil, but what about this material here? Well, I made a cast of this and brought it back to Riverside and recast that. And you can see these features here, these little lines that are radiating, and they're very regularly arranged. They're too regular to be something inorganic. You can also see these other funny wavy lines that are occurring here. And I began to realize that this was a piece of a soft-bodied Cambrian fossil. Now, you may have heard Ritesh was talking about the famous Cambrian Burgess Shale, where not just the hard skeletons of fossils are preserved, but also the soft tissues. Well, this is India's first soft-bodied fauna from the Cambrian. Wow. It's an animal that is found widely in the Burgess Shale and in China, in Kunming, called an Eldoniid. They may be related perhaps to echinoderms, probably free swimming. And you can see these radiating arms, just like, or radiating ridges, just like we had in that fossil. Another thing that's very diagnostic of this is that when the animals settled on the seafloor, they were invaded by burrowing organisms that started to eat their insides, just as we saw in the specimen from the Spiti Valley, from the Parahio Valley. So this is an example, again, of why museums are so important. A specimen that Reed didn't have the knowledge at that time to understand was soft-bodied, now can be interpreted and understood, and an important link, and India's first Cambrian soft-bodied fossil. So very important to have museums, but of course, very exciting to go to the field, and what an opportunity. And here we are crossing the Parahio River. That's S.K. Parcher from the Wadia Institute in the field in the Parahio Valley of Spiti. And we thought we were sort of brave doing that, but here are the poor donkeys crossing the river in the same way. Fantastic place to work because being high and in the rain shadow, the exposure of rock is very good. This is the lower Paleozoic succession. The Cambrian rocks at the bottom here shown in sort of black and with these red beds occurring in them. The Cheyenne formation, very characteristic purple. Then we go into the Ordovician and Silurian, and then the famous Muth quartzite at the top there. And our work is very traditional. We climb up the sides of the mountains. We record the fossils and the sediments, and this is going up. And now you can see that Muth quartzite, the thrust of the Muth quartzite, as we are going up in elevation. Hitting the rocks with a hammer and collecting fossils. I am not smoking a cigarette there, that is a pencil, but traditional work collecting the fossils, and great fun to do. After that, of course, we bring the material back. It is reposited, our specimens are reposited in the Wadia Institute. They've been described here in California, but returned to India. And we have the pleasure of describing them. So this is some very interesting, what's called small shelly fossil material, spines of an animal that lived on the seafloor called the Chanceluriid that looked like a cactus with spines sticking out. This is named after our friend and colleague Dhiraj Banerjee. Here are brachiopods these small shells that are found by dissolving the rocks in acid. But most of the fossils that we are interested in are trilobites. And this is not a Himalayan trilobite. This is one from the Czech Republic. But I put the picture in just to remind you of the form of the trilobite, and that most specimens we find are disarticulated pieces. They are pieces of the hard skeleton that have separated. And so what's shown here are parts of the central part of the head of the trilobite, and very rich in characteristics. And we can see at different levels that we have different fossils occurring. So this is how we can divide up the Cambrian finally by the particular fossils that they contain. Pracheen, therefore, pracheen in Sanskrit and Bangla, old, of course. It's a great privilege to be able to work on this, to name it after fossils after people we admire, like Erwin Vargav and our dear friend Shamli Kostagir. And of course, we find different fossils at different levels. I don't want to go into detail of all the different fossils that we find, and all the kutinati, as it would be called in Bengali, but I just want to say that there are different types of fossils at different levels, and many of those found in India are very important. Red lichia, for example, well-known international standard fossil for Gondwanan localities. Erythrocephalus indicus, the official base of one of the series of the Cambrian, is defined by the first coming of this fossil from the Himalaya, first named from the Himalaya. So very important geological contributions based in the Himalaya. And I am not, of course, an Indian geologist, but I am a geologist of India. And one of the things that I am pleased that has happened as a result of our work is that a reasonably well established stratigraphy, order of successions of fossils for the Cambrian has now been established. And I think I show that in the, oh no, I removed that slide because it was too much detail. But we do now have a international zonation for the Cambrian of India that can be correlated with other regions of the world. Now, what I want to talk about is how we use this to answer the questions that we were talking about the relationship between these different places. So this is famous Pukhtal Gompa in Zanskar. And I want to point out that Pukhtal Gompa is built into this red or yellow kind of rock that is called a dolomite. And that rock sits on top of a very thick succession of sandstones and shales and minor dolomites that contain trilobites within them, Cambrian trilobites within them. So here's the blue zone. We're in the Tethys Himalaya, that northern zone. We've got fossils. That's what happens in the sedimentary rocks there. We've got this 300 meters or 250 meters of dolomite sitting on sandstones and shales. Now remember that one of the things that Desels and co said is that these blue zone rocks sit on top of the red zone rocks. So now let's examine whether that's correct. So let's go along the Himalayan mountains to the east to a very famous mountain, Sagarmatha or Chomolungma, or also known as Everest. And this is looking at Chomolungma from the north side. And here's the top of Chomolungma. And you see this gray rock, which is Ordovician limestone. We'll talk about that a little bit later. But notice that below that is the famous yellow band, which is about 250 meters of dolomite. Very much like what we saw in Karsha with the temple, the monastery at Pukhtal Gompa. And that dolomite, that yellow reddy dolomite, is sitting in on Chomolungma on top of thousands of meters of sandstones and shales. So the succession is very similar to that which we find in Zanskar, but these rocks are not part of the Tethyan Himalaya. They are squashed and deformed rocks that are part of the Greater Himalaya. So we have rocks in the red zone that look very like the rocks in the blue zone, but one set are metamorphosed and the others are not. Now that shouldn't be the case if Tehsil is right, because one group, the blue, is supposed to sit on top of the red. Well, can we test, is there a way to test whether these are actually the same set of rocks in the two zones, one of which is deformed and the other is not? Well, yes, we can look at the ages of those detrital grains. And that's what's done here. We've taken a sample from the trilobite bearing beds just below the Puktal Gompa in the sandstones. And we've taken a sample from Chomolungma, just a little bit north where the rocks are a little bit lower exposed, and compared the two. And I like to argue that these distributions of ages of grains are very similar in both. This one is supposed in the Tehsil's model to be younger than this one, but in fact, the ages of the youngest zircons are almost identical, and the populations of ages are extremely similar. So we would argue that the red zone is just rocks of the blue zone that happen to have been caught and metamorphosed in this particular region in Everest area, whereas in the Tethyan Himalaya, they've escaped that fate. So that's a questioning then the relationship of the blue zone and the red zone. Let's talk a little bit then about the green zone, the Lesser Himalaya, and then further to the south. I don't want to go into this in much detail, but just to say that there are places where we can collect Cambrian trilobites in various of those regions, not only in the green zone, but also the Salt Range of Pakistan has Cambrian rocks, and even in Dulmera in Rajasthan, rocks of Cambrian age. So this is the power of the Cambrian, because we can compare these rocks together. And without going into details about this, when we look at rocks of Cambrian age from Rajasthan, from the Salt Range of Pakistan, from the Lesser Himalaya and into the Tethyan Himalaya, what we find is that those that are in Rajasthan are relatively shallow water. Those that are in the Tethyan Himalaya are deeper water of the rocks of the same age. Why? Because the sea deepened to the north. On the northern margin of Gondwanaland, there was a coast and it deepened to the north. But when we look at the detrital zircons that we get from each of these places, what we see is lots of relatively young grains in the Cambrian rocks that are occurring, whether they're in Rajasthan, on the Indian Shield, peninsular India itself, in Pakistan, in Himachal, or even along as far as Bhutan. So the idea that there are no young zircons in rocks that are truly of Indian origin is clearly not correct, because here in the heart of India itself, the part not even part of the Himalaya, we see these Cambrian rocks containing these young zircons. So I think that answers that question quite conclusively. And this then is a sketch to show what we think the northern margin of India looked like prior to India's collision with Asia. And here is the places where the major faults that now occur, the boundaries between those zones that I've been talking about, are superimposed upon that. And for this talk, I can't go into the details that distinguish these different regions, but this region in particular marks the kind of the edge of, in the Cambrian and time shortly before that, the edge of a carbonate platform, and some particular things that were going on in this region that's now part of the Lesser Himalaya that have important implications for the history of India as India collided into Asia. There are interesting stories to tell and interesting things to think about the history of how, as India moved northwards, so as Peter said, a series of faults start to pile up material as the Indian margin is compressed. These faults, as what is called break to the south. The material piles up, enough of it gets piled up, and then there's a new fault appears further to the south, and this stacking of rocks occurs in the Himalaya as the compression continues. And there are some important properties of Cambrian rocks that allow us to understand some details of what's going on as India collides with Asia that are only interpretable if we know what the original geology of the Himalaya was like before India collided with Asia. So that's really as much as I want to talk about of the academic kind of aspect of this. But I'm very keenly aware that I am and our colleagues are guests in India when we do our fieldwork. As was mentioned, we are interested. I did have the good fortune of spending time in Chandigarh many years ago. I have many friends from that time. And we were interested in the idea, as you are, of sharing geological information with people in India who don't necessarily have the privilege of geological training, but nonetheless may be very aware of the world around them. So this, the book there in Bengali, of course, is what's called a place-based geoscience educational story. And that is telling a story about a region and something that's real to that region. And something that's very common in many parts of India, various different ages, is fossilized wood, petrified wood, or gachpator in Bengali. So here's a piece, and it's curious material. It looks like wood, of course, but it's made of stone. And this is very familiar to local people who live in the rural parts of India. Of course, if you live in the city, you don't know about it. But if you live in the rural part, here are, of course, the village kids, and they know all about where to find gachpator. It is, of course, interesting and strange material. It looks like wood, but it's made of stone. And here it is being revered as a takur in Gosha Char Dukan, my favorite tea shop. And you can see, of course, it being dressed with flowers with reverence, because people know that this is something special. Of course, in Hindu tradition, locally, the interpretation of this is Ashura, the bones of the Bakashur from Mahabharata that is slain by Bhim. But in Muslim tradition, there's a local story about a Muslim saint here, Kamani Baba, turning wood into stone. In Adivasi tradition too, there are stories. So each of the traditions has an explanation for this curious material. But in our story, Monisha wants a natural explanation. A very bright girl, village girl, and she wants to find an explanation for how this strange material could form. So she's a very bright girl. Here she is up a tree. There's a tube well being drilled in the village. She learns about the different levels, different rock layers, sedimentary layers, and their water carrying potential. This is right up Ritesh's alley. She has a series of incidents, and this is in the hot springs at Bokashar, where she takes her Takuma, her grandmother, and into the hot springs, and her grandmother slips, and she grabs a a post, a wooden post, and gets a splinter in her finger. She takes the splinter out and it falls into grains of sand. Because, of course, in the hot, brine-soaked waters, silicious waters of the hot spring, the wood is being transformed into silicification, into silica, and the Gatpator process is happening. So she finds a natural explanation for how this transformation can occur. Her shari is wet. She gets a fever on the bus on the way home. And that evening, in her feverish state, she is visited by a hathi, by an elephant, except it's not a hathi. It's a Chatodonti. It has 4 tusks. It's a Gomphothea from the Maya-Pliocene boundary. And the Gomphothea takes her on a journey back in time to view the village as it was at the time of the Maya-Pliocene boundary. And she meets, characterful fossils like Shivatherium and a Jolohoshti with the nose pointing down, not up. And she notices these differences in the animals at that time and the environment at that time. She's chased by a saber-toothed cat, of course, and returns, her fever breaks, returns to tell the story and to share that with her family. And the sort of light of science in her eyes. So we had a great time doing programs related to this story in various institutions and schools in India and Bangladesh too. And this is doing that. I took 2 students from here, my university here in Riverside, UC Riverside, 2 ladies of Bangladeshi origin. Happily, one Muslim lady, one Hindu lady, which was nice. And here they are talking about the differences between the modern elephants and the Gomphotheres. It was, children are so magnificent and so curious and so lovely in India that it's just a pleasure to do this. The story was dramatized by a theatre group who toured around and did a play about it, which was very nice. And about a year later, friends did a survey to see what the impact of this book was, because we were interested to see whether the children retained understanding from the book that they had been given. And we did a study which we published in the Journal of Geoscience Education on this. And what we learned was very interesting, and that was that if the story was read to the children, they could understand it completely. There was no problem. But the reading challenge, the level of reading comprehension necessary to understand the story was a challenge. So while if the story was read, they could get it, it was hard with kids in the rural environment, the rural setting, to be able to access the story. And that is what has made us think about our latest scheme that we're working on and trying to get the funding for, is to produce a geoscience educational outreach, place-based geoscience educational outreach that tells the story, which is, of course, India's movement northwards, this incredibly dramatic story of the subcontinent moving at 20 centimeters a year northwards for its collision with Asia. But to do this in a way that doesn't involve reading, and that means making animations. And in fact, it was animation of plate tectonics which first intrigued me as a 10-year-old boy in the early days of plate tectonics. And so our plan is to produce an animated serial called in English, but it would be made in Hindi, Urdu, and Bangla, and maybe a South Indian language too, called in English, The Ocean on Top of Our Mountain. And of course, that's being the fact that the top of Sagarmatha is actually Ordovician limestone. And so the top of the world's highest mountain is originally a sea floor. And so the ocean on top of our mountain. And briefly, the story for this then is that in our story, a climber, a real climber, Captain Shipra Mujumdar, collects a fossil, Gutushuti, on the top of Everest and gives it to a young girl. So we had Monisha in one story. So this girl is called Nusrat. And in Nusrat's warm hand, the trilobite unrolls and comes back to life. And Gutushuti, the trilobite, takes Nusrat on a journey, on a cloud, and they visit various parts of the Indian subcontinent through time. So of course they leave the Himalaya and go southwards to Madhya Pradesh and look down on the charismatic fossils, the Rajasaurus and the Iosaurus, and all the exciting things that are happening when India was an island continent on its journey northwards. And then, of course, there's the magnificent, this is a little bit of the animation of it, the magnificent story that Ashok Shani and colleagues have been so intimately involved in, the beautiful transitional series of fossils from 48 to 40 million years ago, showing the evolution of whales. So this, of course, is just absolutely treasure of paleontological transformation, seeing these fossils that from their ear structure are clearly related to the totally aquatic group, the whales today. So we know that these animals, these ancient fossils, are whales, but they are not whale-like in their limbs. We can see that limbs that are clearly adapted to living on land and not in the totally aquatic environment. And furthermore, of course, looking at the ankle, we can tell from the structure of the ankle bones, the astragalus, that these are artiodactyls related to animals like deers and hippos. So connecting today's totally aquatic group to their terrestrial origins through these animals. And of course, as India collides with Asia, the Himalaya starts to rise, the area in front of it, the Indo-Gangetic plain sinks, it becomes more aquatic, and in this environment, there is the transformation. So our story takes a little help from one of the most beautiful and classic Indian stories, Indian pieces of literature, and that is Kalidasha's Meghdut. And of course, it's just by happy coincidence that the locations of Gutushuti up in the Himalaya and the dinosaurs in Madhya Pradesh and in central India, and then the whale fossils. If you look at the root of the cloud in Kalidasha's Meghdut, these fossil localities lie exactly upon it. So, of course, in Kalidasha's story, the cloud is sending its message of love to the beloved who is separated in the Himalayas from the Yaksha down here. But in our story, of course, we do use a cloud, but the messenger itself is not the cloud, it's the subcontinent. It's India that is moving northwards for its tryst with destiny and its collision with Asia. And so this is an incredibly dramatic story, just as these classics of literature are written down in layers of Talpatalipi. So the real history of India, what nature itself says, a history that is common to all persons from the Indian subcontinent and shared by all, is written down in layers of rock. And it's a history that that anyone who's been fortunate enough to be involved in the natural history of that region can be proud of. So this is our plan to produce this and to distribute for free this story as 10 episodes on the internet, and we are trying to do that. But I should say that this is in association with the National Institute of Design in Vijayawada, my friend Shekhar Mukherjee and Trisha Banerjee. So with that, I'd like to thank you, Ritesh, so much for this invitation, and I'm very happy to be here.
Thank you, Nigel. It was a very, very interesting talk, I must say, very lucid. And the way you explained the movement of India and its journey was very fascinating. The Cambrian and the Trilobites, how you could relate it so interestingly, was really a turning point, I think, in the understanding of plate tectonics also, because we always see India moving, but what was happening when it was not moving? That is what you systematically put it. And what the positions of America and India, and then finding these fossils right in Himalayas, as you showed the locations. And interestingly, I was in Chitrakoot. It is like a very fascinating place, And
yes.
then there was some stromatolites, colonies of it, beautiful.
Yes.
I could find some 6 feet stromatolites, and then a lot of interesting structures, So the life at that time, and the trilobites, as you mentioned, in different parts of India, Pakistan, and extending right up to Bangladesh and Bhutan. So, and then we, as you said that, I cannot remember the name of Everest, what you said, but like, what was it?
Well, I think the Tibetan name is something like Chumulungma, and of course the Himalaya range. I think the high mountains, Sagarmatha is used in Nepal, but I think Sagarmatha is used for not just Everest, but for the sort of the high range. But of course, these are the George Everest was a British character, so it's nice to try to use the
local names. Yes,
people call them locally.
So now I just want to ask a few questions which I have in my mind, and they were like, if we are finding these the Tethyan Basin, we call it as like the paleolatitudinal positions of these, the ones we are finding in the Everest, or maybe in the Himalayan range, which you said, the entire Himalayan range, the Tethys sequence. So this sequence, does that mean that the entire Tethyan sequence, what we understand from your talk, was like everything which was of those age, or how would you define the Tethyan sequence in totality, in terms of age, whether we should call these Paleozoic sequence or the Precambrian Cambrian sequence? We are also finding some Precambrian sequences in Himalayas and the Cambrian sequences.
No, so thank you for the questions. Good one. So it's certainly the case that the Tethyan zone has a lot of rock that is Paleozoic in age, and Mesozoic, and Cenozoic, tertiary too, in age. So in that blue zone, or rocks of all those ages occur, and the squashed, deformed rocks of the Greater Himalaya certainly, I think we've shown in the talk, contain some rocks that were originally Cambrian, and probably some that were a bit younger. And then we come to Lesser Himalaya, and most of the Lesser Himalaya is much older, is billions of years, or a billion years or so old, and old rock. But there is this part called the Outer Lesser Himalaya that has rocks of Paleozoic age and Mesozoic and and younger too. And then, of course, we come further south. In India, we have the Shivalics and that tertiary age. But in Pakistan, we've got this little sneaky piece of Cambrian sticking out there in the Salt Range. The first part of the Indian subcontinent to be recognized to be Cambrian, actually. And then now recently, thanks to discoveries by Indian geologists, the age of Cambrian rocks in Rajasthan. So yes, it's certainly true that the majority of the Paleozoic and Mesozoic successions and the most continuous successions are up in that Tethyan Himalayan region. They're the most continuous because that was sort of offshore. That was the deeper water. The Rajasthan, of course, is shallow when the oceans were crossing the Indian continent at high sea levels, but still a very shallow sequence and a very thin sequence. But to the north, there's more what's called accommodation space, more space to build up layers of sedimentary rock. And so we've got that good record in the Tethyan Himalaya. So yes, different geographies, different paleogeography, different conditions, different paleo environments of rocks of the same age, and also the preservation in the southern part of the Himalaya of some of this very much older rock that we don't see in the Tethyan part.
Mm-hmm. This brings to another question, like you said in Shivalics. So making the boundary of Tethys on the basis of the Tethyan sequence which you showed, and then separated by main central thrust and then main boundary fault, and the other one was like the intersanctus, which is what they call it, and then the south of it and the central thrust actually is like the Tethyan sequence. But now we were doing some studies. We were also just trying to find this marking these boundaries, of the southern boundary of say Tethyan sequence in the Himalayas. So as low as near Chandigarh, we were able to find these limestones, and these limestones are stromatolitic. So this is near Chandigarh I'm talking about. So after that, we have this sequence of say Subathu, Dagshai, Kasauli, and then we have the Shivalics.
Yes.
And so the sequence of this limestone, stromatolitic limestone, a huge, and there was a cement factory about 40 years back, running on that. So this actually is also according to if we can try to reconstruct the paleogeography. So then the southern boundary of the Tethys sediments which you are finding comes to be near Chandigarh. And then we have then like defining it on the basis of these thrusts and what is like something like yes, it is good to show it schematically, but when you see practically on the ground, so it's like we have stromatolites right near Chandigarh, and above that we have this adjacent to that we have this Shivalik sequence, and then with the boundaries of Subathu, this nummulitic limestones and or whatever characteristics are of Subathu formation, we are getting that, and marine and non-marine sequence there. So my question is, and then the other thing is like since I worked and you have worked a lot in Zanskar and Spiti, and but if you see there's then Zanskar range is also like you show that Fuchtel monastery, and that was quite interesting. You're getting trilobites there, so that could be a place where geotourism can be promoted, or some geoheritage sites can be developed, so that people can just know that wow, this is what the ancient origins of this is what how the Fuchtel monastery and actually I was just trying to correlate when I was in Chitrakoot. I was shooting for this Discovery Channel, and then we found this. This was already known, but we found very interesting things. The Archean sequence and this So one time the origin of Earth, the rocks, and then the origin of life, both lying one another, and then Chitrakoot becomes such a famous place. Similarly, the Puktul monastery could be like a religious place, and then also why they chose this Puktul monastery. There are so many monasteries, and there are so many evidences of fossils related to that. We found this Hues monastery. We got a lot of fossil logs of trees there. Then we have this Mathu monastery. I found fossils there also. Then Basgo monastery, I found fossilized wood, and then they're very beautifully preserved there. Now linking these two could be very interesting, but
Yeah.
and just the stories later on which you told about how you are making comics out of it, and then plays out of it, and then documentaries or 10 series of it. This is like very interesting, very interesting, and that is like making this geological sequence very popular.
Well, I think, yeah, thank you. So yeah, I mean, two parts to that. Yes, I mean, we do feel very much that the story of India's geology is something that is part of the subcontinents and the nation's history, and something people should enjoy and be proud of.
Yes.
There's no part of the world like India that has such an exciting geological history, and so this is something that people would be nice for people to know. So yeah, that is very important to us, and wanting to share the pleasure that we've had in our understanding. So yeah, that's extremely important. To come back to your first part, so you're absolutely right that so these issue of, say, rocks with stromatolites and the Subathu sitting on top of those, and so there is an enduring debate about the structure of the Lesser Himalaya, and whether in the Lesser Himalaya there are different regions within the green zone in the story, the outer and the inner Lesser Himalaya, and their original relationships. In our view, the outer Lesser Himalaya, which is now to the south, so the Prol Tal region, is material that did originally sat further to the north and has been slid southwards over the inner Lesser Himalaya. And certainly that kind of relative movement of regions has occurred. But it doesn't really make any difference to the overall story, because in the Salt Range in Pakistan and then in Rajasthan itself, we see clear evidence of Cambrian rocks with affinities that are very similar to that of the Tethyan Himalaya, occurring as far south as those regions. So the details of the sort of the original geography of the margin are debatable and difficult to resolve, because most of these rocks have been eroded in the Himalaya, or many of them, especially in the Lesser Himalaya. But nonetheless, it is clear that during the Cambrian there was a wide shelf that extended from Cratonic India northwards, and that was the basic paleogeographic situation that occurred. And there are lots of spirited debates that go on. We enjoy one with great Owen Vargav on this issue, but I think it's very clear that from the remnants of rocks that are left behind, that there was once a much more extensive coverage of Cambrian rock that has been eroded away.
That is what I wanted to ask. Like, has any study been done about the on the basis of trilobite, the paleogeographic reconstruction, and the map which you showed was like all the continents, all the landmass was rather united at that time during Cambrian time, or whether it was like some segregations or one landmass. And then whether the fossils which we are finding in like the Rajasthan fossils are almost like similar to the Himalayas now.
Yeah, right.
And
yeah.
and maybe these Cambrian fossils which you are finding here may be similar to something which we are finding in Antarctica or Australia or maybe Africa or maybe America. So maybe this is one at that time.
Yeah, well, I think we have certainly recovered, and I talk about the general geological community,
yes.
In our work included, but many others too. That the exactly as you say, the types of fossils that we find, the particular varieties of trilobite, for example, just as today different animals and plants live in different parts of the world, so in the Cambrian. And the famous Redlichiid province. So when we think of that geographical reconstruction 500 million years ago, and we see all the Gondwanan continents together, that is supported, that reconstruction is supported by the presence of a group of trilobites to which the general name Redlichiids is applied, that are found in that Gondwanan continent, but not found here in North America or in Baltica. And that's part of the reason why they're reconstructed as island continents separately. So the distributions of fossils and ancient fossils comes very much into play in reconstructing what the geography of the world looked like. Paleontology is particularly important in this, because we have many tools for reconstructing the ancient paleogeography, but most of them relate to our understanding of plate tectonic processes kind of directly. What's a suture zone? What are the features that we can use to infer an ancient suture? Paleontological information is sort of independent of that. And we can, in a way, we can test reconstructions based on other geological information against what the paleontology says, what the distributions say. So it's very, I think it's very powerful. And I also think that there is a tremendous opportunity in India for paleontology because paleontology is sort of, in some ways, in the late part of the last century, went out of fashion because there are lots of clever techniques like dating detrital zircons and things of that kind. But what actually we find is that we need this information on time. We need this information on stratigraphy in order to test these exciting ideas. It's only through a knowledge of stratigraphy and the independent ability of trilobites or other fossils to date rocks that we are able to test these exciting ideas based on sort of tectonic models. And of course, people, scientists in India have more opportunity to spend longer time in the field and see more rocks and gather extensive collections, which are what is necessary for really doing this work well. So I really see a strong potential in India has this magnificent geology, and doing this stratigraphic geology well and comprehensively will contribute enormously to our understanding of the world's most important mountain chain.
Yeah, I definitely agree with you. Indian geology is like very interesting, and then we need a lot of paleontologists coming, and I think Punjab University and Bavaria Institute, they are doing some good work in this aspect. And but again, I'll just come back to the question of this webinar was like the timing of closure of Tethys. Number one, that is quite important because when India was moving like an island after drifting from the Gondwana land and moving like an island, so maybe these sediments were accumulated in the ocean floor or were fossilized and then they were just uplifted there. They were the paleolatitudinal positions, like we have now very interesting papers on by Americans and collaboration with the. They say that the Khardungla, the Khardung volcanics, and then the paleolatitudinal positions based on those were like 11 degrees or something like that, north of equator. So if that is the situation, then that means then if Khardung volcanics and then the whole situation, then the Zanskar section or the Spiti sections, they are also paleolatitudinal positions. If that is true, because we can't rely on that until unless the entire theory of plate tectonics is based on fossils, and the
Yes.
others just substantiate until unless we get some good evidences like Spiti fossils and now Rajasthan fossils almost same, and then bringing that back to Rajasthan equator, or maybe how we do it, that is another thing. But fossils won't lie. That
Yes.
is very interesting, because any instrument or any zircon, yes, it has been traveled and then you can just date it, and then, but the timing of collision, now very important. When the sea collided, it is like based on again 50 million years generally accepted. Some they take it to around 40 million years. Some now reserved take it to around 30 million years, but not 28 they say is okay. And then one aspect would be like the closure of Tethys Sea. So now defining Tethys Sea is like now we are finding stromatolites with the Subathu, Dagshai, Kasauli, and on the other side we are finding it with the upper Shivalik formations also. The other side of this stromatolitic band, which we just recently found, and then we were just trying to just figure out, sitting in this COVID situation, the nearest outcrops which we go. So this was quite interesting now. So now on one hand, we have these stromatolites here. Then we have then Karols in Solan. And then there also we have some good stromatolites and trilobites in Spiti. And then Nahan also some, so, and Zanskar. So my question is, when all these aspects, now we don't consider them, maybe these are all near the equator, something very near to the Gondwana land. And when the Indian plate started drifting, they started drifting from there only, they started drifting from there. Instead, like putting it here. This is my question, like, is it because now if you're trying to bring Khardungla volcanics to equator, and then you are trying to bring the entire Himalayas, and interestingly, I just want to make another observation, and this is based on my research, like the fossils which we are finding in Kasauli of plant fossils, they are about 6-7 species which we found were not found in Himalayas. Now they are restricted more to Andaman Nicobars and more towards Malaysia and Indonesia. So this similarity, because at that time when I was doing my research, I was not able to understand this. But when I went to Ladakh and found similar rocks of fossils equivalent to Kasauli formation and huge logs of woods just south of Indus Suture, and then correlating these two brought this entire sequence brings to again to 4 degrees to 4 degrees or 11 degrees north. Now I am also making a working on this paleolatitudinal positions of India based on these plant fossils. So my again question is whether based on this Cambrian record, and yes, it is very nice when it never drifted. And when it drifted, then there are two aspects I want to ask you now, and this question just came into my mind right now, is when it was like one with Gondwana, the Cambrian and the Paleozoic sequence in the fossils play a very important role on land, one aspect of the coastal things. But something was happening on the coast also, at that time. And that is what maybe the Tethyan Himalayan sequence, what we are calling it like Spiti, maybe Zanskar, that was also like in the paleolatitudinal position of those formations were also very near to the Gondwana land. And before movement, before movement and there, and then when it drifted, So its entire mass was drifting, and that is how it was elevated. What do you say about this, sir?
Yeah, I think that's exactly right. Yes, it wasn't just very close to Gondwanaland; it was Gondwanaland. You know,
It was Gondwana.
This was the northern margin of Gondwana.
Northern margin, yes.
Yeah.
So now since we agree with this, so then that means then the sea which was further ahead of it. So this was not the Tethys Sea. This was part of the Gondwana sequence, and then the sea which was ahead of it was Tethys Sea, which we are finding evidences in form of maybe the Subathu Dagshai Kasauli, the Cenozoic sediments, and they were deposited into one of the slides which you showed now 80 million years, the one. So this fits into my model. You know, this theory would explain each and every aspect of the stromatolites and this and this and this, and then we have this Subathu Dagshai sequence in the Kasaulis with the Malaysian, which the 80 million slide. I was really impressed by that slide, and which you showed, you know, and then this paper of MIT, they also are also of the opinion this. So now it's almost like very good, you know. So well, so now if that is true, so my timing would be like if Kasauli formation that we have dated to around 20 million years was near the equator, maybe 4 to 11 degrees north of equator. So Himalayas were not born at that time. The collision was not happened. Collision of India happened with the Subathu sequence, Subathu Dagshai sequence, which was happening, which were deposited here, and then they all were moved ahead, you know. So this could be that. So now I don't know, but this is my observation. You know, I just wanted to discuss. But now, after listening to your talk and getting your assurance, now maybe this could be very interesting. You know, what do you say about it?
Well, I'm very glad that, you know, something I've said has stimulated your thinking on this.
Yes. Because this was like, you know, this webinar, you know, I started because these are the problems which I faced in the field. You know, when it collided, when, and what is the evidence?
There are so many stories. You know, one of the things I didn't talk about today is that, you know, the idea that there were other bits of Gondwanaland on the northern margin of India is, you know, which was sort of the basis of the Tehsil's model, you know, is definitely supported by the structure of Tibet. Is made of, you know, 3 little slivers: the Lhasa block, the Chentan block, and Kunlun to the north. So, you know, when you're talking about Tethys, there are a whole series of oceans called Tethys, Proto-Tethys, Paleo-Tethys, Meso-Tethys, Neo-Tethys. You know, so it's a very fascinating and very complex system. But you know, what one would say is that of all the regions in the world where we see continental accretion occurring, almost everywhere else is way back in the Proterozoic.
Yes.
You know, the construction of Laurentia, the construction of peninsular India, Africa, etc. The only part of the world where in Phanerozoic times, so since the base of the Paleozoic, we have seen continent forming, a major continent forming, is Eastern Asia. And that's why the geology of that part of Gondwana, South Asia and Southeast Asia, is so important because it's relatively recent. We've got a good controls from the younger geological record, and younger I mean Paleozoic and Mesozoic. And so we can really use those tools to refine our understanding of how this process of continental accretion really occurs. So this is, you know, why academically I think the interest in the region is so strong, and you know, you saw this from Peter Molnar's talk and the seminal work that he's done on that. But it is, you know, very encouraging, I would hope, to younger scientists in the region that, you know, there is something really special about this place and this area of the world that can be taken advantage of.
Yes, I'm so happy that The first talk was of Peter Molnar, and he gave the brief idea. And then, see, you agreed. It was like a natural selection of everything putting in place, and we may get a very good answers to this entire concept of understanding the Tethys, in totality. So we have just started with the entire concept about Tibetan Plateau in India, and now you have given a very, very interesting thought and so much information about the trilobite explosion and how that can be actually used, that can be used as a tool to trace the entire journey when it started, and now it is in place there. But how you explain the entire process, that is a journey of India drifting from forming Gondwana part, forming this Cambrian sequence, and then drifting, and then forming the Himalayas. And both these stories need to be somewhat intercalated or put in such a simpler sense, so that it doesn't become anything complex. And the way you have done it, I think the way you portrayed it in the comic form and the play form, and now what you're planning in a form of film, I think this will be a boon to young geologists, not only geologists, but small children. If we can inculcate that interest, as you said that you were fascinated with at 10 years, you said, no?
Yes, I mean it was watching a very early science, sort of general science educational program on the television. I remember the morning I went down the street to play at a friend's house, and his father was watching the television, and it had, this might have been 1974, and it had a very early science program on about what was then called the new global tectonics. It wasn't called plate tectonics in those days. It was too new, and it showed an animation of India moving northwards and raising the Himalaya. And I thought it was wonderful that the major geographic features of the world could be explained in this way that is so elegant, and explains this complicated geography that we see, and shows it to be dynamic over time. And if we're thinking about where we fit and the sense of perspective of ourselves as individuals, what wonderful opportunity to feel a sense of perspective if one understands that we are so privileged to be part of this ongoing and dramatic and extraordinary history of our planet. And nowhere better than India to teach us that.
I'm so happy. I'm so happy that not only you gave this wonderful talk, but you used local languages, local dialect, and the way you interacted with the children, and the scripts, what you're planning in your documentaries. I think that is the need of the hour, and that is actually what we also wanted. How fossils are formed, how fossils are formed in Himalayas, and how we get fossils from the Himalayas. So my expertise was like in collecting flowers, fossils, and like I was inspired by Medlicott because 1864 he came in Kasauli, and then I belong to Kasauli. So I was like, when I didn't know much about geology, but like when I saw his work, when a first year student, first class, and then, acha, he got fossils from Kasauli, but I have lived the whole time, I've never found anything. And then this journey of collecting fossils started. I was not much interested in the studies, but more, how can I get fossils? Then it took me about 2 years. And now I have the largest collection of fossils, from Kasauli. Yes. So that type of information and that type of interest, with your series, what you are planning, I think it's a wonderful step. And the way you presented it was like meant for the museum. I think you spent a lot of time preparing this talk, because it was not a hi-fi talk for a geologist, and everything goes up but it was meant for like inculcating a lot of interest among young geologists, not only geologists, but I think among the children, how the earth looked like and how we can just nurture it, enjoy it, and if we can take care of it, the earth takes care of it. If we understand it more, we will enjoy it more rather than yeah. So I think with this, if you have anything to say, the concluding remarks, I think we will have it, and then we can just end it. Okay.
Well, thank you so much for the invitation, and for the privilege of spending a portion of my career working in the Indian subcontinent.
So, Ocean, you would like to ask something, or?
Yeah, I mean, me being an artist and listening to geology lectures, it's something new for me. But the way you have explained everything, Nigel, it's so invigorating, and so I want to know more about rocks and geology. You have really piqued my interest because you portrayed it so well with these manuscripts and these stories that you had with the children out here. It's really something that I'm looking forward to, and maybe if we could have it be as like a part of a section somewhere in our catalog somewhere, it'll be amazing, because I, as an artist, really look forward to creating stories. So I am very, very intrigued by what you have shared with us, and thank you so much, Nigel.
Well, thank you, Ocean.
I just
I'm happy to.
Ocean. Ocean?
Yes.
So the section of the Cambrian explosion.
Right.
So the poster which we are planning,
Mm-hmm.
So you can we can just make a small draft of it and get all the information and his ideas from him, because I would like now one thing is I would like this the Spiti, the background could be like the Spiti, the trilobites and all these we are finding in the Himalayan region, the Rajasthan region, and the Gondwana region, this Africa. So we construct this background, and on that background we construct all this trilobites and this whatever information what we are planning, Nigel, is it okay with you if you can help us in that?
I'd be very happy to. Yes, very happy to.
So we'll be troubling you a lot, huh? Because we are in the process of making it. So we'll dedicate so that section we will like to prepare under your guidance. Okay, is it okay?
Yes.
Yes, certainly, of course. Yes.
Thank you very much. So with this, I think we close today's talk, and we meet on 22nd. Hopefully everything should work work well like it worked today, and then we can just start if anything happens. Otherwise, then we have this talk.
Good. Okay.
Okay. Bye bye. Thank you. Namaste.
Bye bye.
Okay. Bye bye, Nigel. Ocean.
हाँ जी.
तूने ये जो हमारा फॉर्मेट था, उसमें हमने इंडियन जियोपार्क तो बोलना था.
आपने मेरे को बताया ही नहीं. मैं भी थोड़ा
नहीं यार, ये सारा क्या है कि हमने अपना इंडियन, हमारे को टेथिस फॉसिल म्यूजियम बताना है.
मुझे लगा कि हम बेसिकली वो अलग से रिकॉर्ड कर रहे हैं जो इंट्रोडक्शन वाला है.
नहीं इंट्रोडक्शन वाला नहीं. इसमें क्या करेंगे, चलो अच्छा ठीक है. अब तुमने अब जो ये वाला पोर्शन है जो तुम्हारा वाला, जो तुमने बोला था, इसको दोबारा से तुम अगर बाई चांस जरूरत पड़ी तो हम इसको उस दिन हम दोबारा से अभी रिकॉर्ड कर लेते हैं इसको थोड़ी देर आज या कल में ना.
ठीक है.
और फिर उसमें तुमने मेरे पास लाके छोड़ना है. मैं नाइजल को लेके
जो प्रेजेंटेशन दे रहे थे पहले वाले लेक्चर में, वो आप दोगे दोबारा?
तुम क्या कहती हो? उसको थोड़ा सा रिफाइन करेंगे, उसको रिफाइन करेंगे.
हाँ, रिफाइन करना जरूरी है.
क्योंकि ऐसे नहीं करेंगे, ऐसा करते हैं, मैं थोड़ा सा बना लेता हूँ उसको. कल हम एक बार फिर मिल लेंगे जूम में. जूम में मिल लेंगे और उसमें क्या करेंगे, इसको प्रेजेंटेशन को और टाइमिंग को थोड़ा सा ऐसा करेंगे ताकि ये पूरी अच्छी सी आ जाए, ठीक है ना। और उसमें भी थोड़ा सा लैंग्वेज में भी उसको चेंज कर लेंगे, क्या क्या इंपॉर्टेंट है टेथिस फॉसिल म्यूजियम पर। आज बड़ा अच्छा आइडिया आ गया, ये सारी प्रॉब्लम सॉल्व हो जाएगी हिमालयस की, क्योंकि वो स्पीति के जो फॉसिल्स थे ये सारे हमने वहां पे ला दिए और ये सब कुछ हो गया। अच्छा चलो, बड़ा अच्छा है। अब हम क्या करेंगे, इसको तुमने मेरे पास लेके कल हमने तुमने इसका तो लेक्चर हमारे पास हो गया, और इसको क्वेश्चन आंसर में पहले ऐसा करेंगे, डिस्कशन अच्छी हो जाएगी।
1 सेकेंड, अभी भी रिकॉर्डिंग हो रही है क्या?
शिट